Okay, from now on, we are going to talk about heaps. In the last lectures, we stated we would like to build efficient sets and dictionaries because we could solve numerous problems with dictionaries. And we set a goal to make find, insert, delete, find mean, and find max operations O log n. And we saw how we can make these three operations O log n in the last lectures. And in this lecture, we are going to make the rest of these two methods O log n. And we are going to use tree-like data structures to achieve this goal. And what is a binary heap? In this class, we're going to talk about binary heap. And a binary heap implements a priority queue ADT. So priority queue is the concept, and a binary heap is what we actually implement, the priority queue ADT. And we need to talk about what a priority queue or a binary heap is. They are similar to queue or stack, meaning they are just a collection of elements. However, each element, as the name suggests, this priority suggests, each element additionally has a priority. And an element with high priority is served before an element with low priority. Therefore, in the naive queues or stacks, the order of inserting the items determine the priority. However, in the case of priority queue, the priority is determined in a different way. So these are the properties of priority queue. And a binary heap is a special type of binary tree. In the last lecture, we talked about binary trees. And a binary heap is a special type of binary trees. So what is a binary heap? In the case of binary heap, which is a special type of binary tree, the value of each node must be no greater than the value of its child. So if a node's value is no greater than its child, then we call it min heap. Whereas when the node's value is less than the value of its child, we call it max heap. And I'm going to describe this property with pictures in the following slides. So don't worry about this statement if you don't understand this perfectly. And we call this property as heap order. You need to keep this term in mind. So please memorize this term, heap order. So this is the picture. In the case of min heap, as I told you, the value of this node is no greater than the values of its children. So 2 and 3 are greater than 1. And 2 is smaller than its children, 4 and 5. So this is what we call min heap. And in the case of max heap, the order is reversal. So the value of the node is greater than the values of its children. So 8 and 7. So 9 is greater than 8 and 7. So it's quite easy to understand with pictures. And we need to define heap ADT before we start to implement heap. The functionality of a heap is, of course, we need to be able to construct or create a new heap. And this is very important. This is the subject of today's class. We want to make find mean operation, which returns the smallest element, and delete mean, which removes the smallest element from the set and returns it. And insert item inserts a new element into the set. So heap is a collection of items, and we are going to make this find min operation O log n. And we're going to support len operation, which returns the current size, the number of elements of the set. And before we start to implement heap, I'm going to describe how we are going to implement find min operation. So for binary trees, from this slide, we're going to talk about min heap. Max heap is quite similar to what min heap. So when I just describe min heap, you are going to be able to implement max heap on your own. So from now on, I'm going to focus on min heap. In the case of min heap, the smallest element must be in the root node. I told you that heap is a special type of binary trees, and we are going to place the smallest element at the root node. Therefore, the find min operation is very easy. So we are going to just return the element from the root. Then it is going to be the minimum element, the smallest element in the heap. So implementing find min operation is quite easy if you just keep this property. And insert item is somewhat complicated because we need to maintain that the tree is complete. And what does it mean by complete? A complete binary tree is a binary tree in which every level, except possibly the last, is completely filled, and all the nodes are as far left as possible. I'm going to show you a picture and describe what this property complete means. So if the lowest level is not yet full, we need to add the next open position on this level. If the lowest level is full, we need to add a new node at the leftmost position on the next level. So this is the picture. We say this tree is complete because we do not have other levels unless this third level is full. So in this case, when we want to add a new item, we are going to place that new item at this position, not here, not as a child of 8 or 7 or 9, but the only place a new item can go is this place as a child of 4 to make this tree complete. And if this lowest level is full, there is no more place we can place new items, then we are going to add a new level, the 4th level. And we are going to place new items from the leftmost position here. So this is the next place where a new item can come. And the next item will be the right child of the node 8 here. All right. So that is what a complete means and how we are going to insert new items. And because we need to maintain the heap order property, we are going to have the edit element bubble up the tree until the heap order property is satisfied. To do so, we are going to compare the new element x with its parent. If x is less than its parent, then we are going to exchange x with its parents. Then we are going to repeat this procedure with x and its new parent. So this is an example. So in this case, the heap order property is satisfied. So what was the heap order property? The parent node is smaller than its children. So 4 and 5 are larger than 3. And this heap order property is satisfied throughout all the nodes. So in this case, its children are larger than this node. 8 and 7 are larger than 5. So we are going to keep this heap order property even when we add new items. So let's say we want to add 2 here. Then what we are going to do first is just add this new item at this position. And we're going to make this node bubble up until the heap order is regained. So we compare 4 and 2, and 2 is smaller than 4. So we're going to swap these two values. So like this. And at the next level, which is the second level here, we're going to compare 2 with its parent 3 again. And because 2 is smaller than 3, we're going to swap these two values. Then 2 will be a new parent. So this is how we are going to maintain the heap order property when we insert new item. And because before we add this new node 2, the heap order property was satisfied throughout all the nodes. And if we just make sure that the new item makes the heap order property, keep the heap order property, then all the other nodes will follow the heap order property. So we don't have to worry about other nodes. We only need to care about this new node. And this is a picture. When we add 70, we just swap until it finds the right position. So because 70 is smaller than 120, it goes up. And because it's smaller than 80, it goes up again. However, it is larger than 10, it just stays there. So we're just repeating this procedure until we find the right place for the new item. So that is what insert is about. And how can it delete the mean? Because the mean value is at the root, we're just going to remove the node or the value at the root node. And we're going to fill the hole because we remove the value at the root. It's going to be a hole because there is no value. And we're going to fill the hole with the last entry in the tree. And we are going to bubble X down the heap. So in the case of inserting new item, we are bubbling up this new item to find the right place. However, in the case of deleting mean, we're going to delete the value at the root, and that is going to create a hole at the root. And we're going to fill the hole with the last entry in the tree, and we're going to bubble down the X value to maintain the heap property. And if X has a child that is smaller, then we're going to swap X with the child having the smaller element. And compare X with its new children. If X still violates the heap order property, then we're going to repeat this process again and again. I'm going to show you a picture. So in this case, if you want to delete mean, then the mean value is at the root position. So we're going to just delete this value and it's going to create a hole. And we're going to replace this hole with the last entry. The last entry is at the last level and the rightmost value. So let me say it again. The last entry of the complete tree is at the rightmost node at the last level. So this one is at the last level on the rightmost side. So this is going to be the last element that goes to the root, like this. And we're going to compare this value with its two children. And because 4 is smaller than 6, we're going to replace 4, and 6, and 4 goes up. So we are bubbling down 6. So we compare these three values, and because 4 is smaller than 6, 6 goes down, bubble down. And we compare again, 6 and 5, because there is no right child, we are not going to compare this value, but these two values. And because 6 is larger than 5, it goes down once again. And after that, the heap order property is satisfied. So in this way, we're going to delete the mean value from a heap. So from now on, we are going to implement a binary heap. But up to this point, do you have any questions? All right, no questions. Okay, let's implement a priority queue together. First of all, we are going to talk about how we can implement a priority queue using simple Python list. So in this class, we are implementing priority queues. First, we're going to use simple Python list, and then we're going to make develop this Python list so that our priority queue will have O log n computation. First of all, let's define priority queue. And we're going to implement the constructor first. And we're going to maintain a list, and we're going to store all the elements inside this list. And I told you that we need to implement this insert method where we can insert new item. We're just going to append this new item to our internal list. That's what we are going to do. And we need to implement find mean. We're going to return just mean value from this list. Okay, it's very simple. However, you need to be cautious about this. Our goal was to make this operation log n is the number of items inside this heap. However, it takes O n rather than O log n. And we're going to make this operation O log n towards the end of this class. In another method we need to implement is delete mean. We're going to first find the mean value and its position. That's what we first need to do. Then delete the mean value. This is what we need to do. And this is our first PPP exercise.